Hi guys, welcome to my channel. In this video, I'm going to talk about some questions for elastic strings and spring. Okay, the first question will be application of strings in a slope. A particle of mass 0.5 kg is attached to one end of a light elastic spring, which is really important, of natural length 0.9 meter. So L is equals to 0.9 meter. And modulus of elasticity, lambda Newton. Okay. The other end of the spring is attached to a fixed point O on a rough plane. Rough plane means there's a friction, which is inclined at an angle theta to the horizontal, where sine theta is equals to 3/5. The coefficient of friction between the particle and the plane is mu equals to 0.15. The particle is held on the plane at a point which is 1.5 down the line of greater slope from O, as shown in figure 2. The particle is released from rest and first come to rest again after moving 0.7 meter up the plane. Find the value of lambda. Okay. The first thing I would think about this is I can use conservation of momentum, because before the particle moves up the slope, it has a certain height from the ground, so which means it has gravitational potential energy. And the string is stretched from 0.9 meter to 1.5 meter, which means there will be elastic potential energy, because the spring will try to return itself to its original length. Initially, the particle will have gravitational potential energy initial plus elastic potential energy initial, and it's equal to, okay, now here, in order to understand the final situation of the particle, we need to draw a diagram. And the diagram doesn't need to be same, like exact the same. You just need to draw somehow similar. So it moves up 0.7 meter, so what left is 0.8 meter. So initial point, and it moves up 0.7 meter. And don't forget, there will be friction opposing the motion of the particle. After the particle moves 0.7 meter, it still have gravitational potential energy. And because the spring has been compressed from 0.9 to 0.8, so the spring will still have elastic potential energy. Also, this is final. Okay, so now we can write down all the equation. Oh, there's another work done that we need to consider about, is the friction, work done on friction. So plus work done on friction, and the formula for it is the force of friction times the distance moved, which is this 0.7 meter. Okay, so here we got initial height and final height, but it's not given in the question. So what can we do? The easier way to find the height is to find the difference in height. And how to find the difference in height? So this is the difference in height, right? And we know this theta. So by using sine theta equals to difference in height divided by 0.7, so the difference in height will be 0.7 times, since sine theta is 3/5, so we can write the value in, will be equal to 21/50 meter. Now we're going to arrange the equation. So since we know the difference in height is the final height minus the initial height, right? So we can take this to the right side. And then we also can take this to the left side. So what we get is mghf minus mghi plus f times s. Okay, now we can factorize the lambda. X squared, sorry, this is minus y squared over 2l is equal to mg hf minus hi plus f times s. And since we know hf minus hi is equals to the difference in height, okay, so now we can sub all the value in. But first we need to find x first. Okay, so what is x? X is the extension of the spring. So it extends till 1.5 meter. So x will be 1.5 meter minus 0.9 meter. So x will be 0.6 meter. For y, it will be the compression of the spring, which means 0.9 meter minus 0.8 meter, we'll get 0.1 meter. So for the friction, it will be mu r, and mu is 0.15, right? And r is the reaction force. To find the reaction force, we need to know the component which is opposite to the reaction force, and this force can be found by using weight. And since we know this is theta, so we can resolve this into mg cos theta. So it will be 0.5 g. And what is cos theta? Okay, so since we know sine theta is 3/5, right? So by drawing the trigonometry and using Pythagoras theorem, we know this is 4. So cos will be adjacent divided by the hypotenuse, so it will be 4/5. So here I will mention it again. The r is the mg cos theta. It will be equals to 147/250. So we have all the information now. We'll sub all the values in. So 0.6 square minus 0.1 square divided by 2 original length L 0.9, which is equals to mg, which is half g, difference in height, which is 21/50, plus the friction times the distance moved by the particle, which is 0.7. Okay, now we got 7938/624, which is equals to 12.7 Newton. Since we use G, right, and G is two significant figure, we must use the minimum significant figures we have in the question or in the working. So it will be 13 Newton to two significant figures. Okay, now the second question. One end of a light elastic string. Okay, now it's string. So there will be no compression in this question. Of natural length 1.5 meter. So L is equals to 1.5 meter. And modulus of elasticity of 14.7 Newton is attached to a fixed point or on a ceiling. A particle P of mass 0.6 kg is attached to the free end of the string. The particle is held at O and released from rest. The particle comes to instantaneous rest for the first time at point A. Initially, the particle is held at here with the string, and the string is slack since it doesn't have compression. Okay, and then it released the particle. So yep. OA, find the distance OA. So here we actually can use conservation of energy. Okay, why? So before the whole situation, we have the ball, which is at a certain height. Okay, so here let's take the ground as an origin. So which means this particular position will be H initial, and after it drops to a certain height, to a certain point, which is A, we call this HF. Here we can see there's a change in gravitational potential energy. Okay, so this ground you don't actually need to draw, because for me, whenever I do gravitational potential energy, I always try to find the difference in height instead of the height for each particular point. So it's much easier that way. So initially, the particle has gravitational potential energy. It doesn't have velocity, so it doesn't have kinetic energy, and it doesn't have compression on the string, so nothing else, equal to the final, which is the HF. So there will be gravitational potential energy, and what about the kinetic energy? Because it is instantaneous rest, so which means the kinetic energy will be 0 too. And what else? There will be extension on the string because it's pulled by the particle, so there will be elastic potential energy. So we can say the distance OA is actually the original length plus the extension X of the string. So the difference of height, we know it will be HI minus HF. Okay, here I will use HI minus HF. So when should you use HF minus the other one or HI minus the other one? So here's what I think. In this particular case, by using HI minus HF, I will get a positive value because HI has bigger value than HF. Okay, so here we know that the difference in height is 1.5 plus x. mghi equals to mghf plus lambda x squared over 2l. So here we can bring this to the left. So we got mghi minus hf is equals to lambda x squared over 2l. Since we know the mass is how much? 0.6 times g times 1.5 plus x equals to lambda x squared. So what is lambda? 14.7 times x squared over 2 times the original length, 1.5. So we get 147 over 25 plus 441 over 50, which is equals to 49 over 10 x squared. Here we got a quadratic equation. So we can use calculator to find the value of x. So there will be two values, which is x equals to 3 plus 3 square root 6 over 5. Let's approximate to 2.07, and the other x, x1, x2 is 3 minus 3 square root 6 over 5, approximate to minus 0.87. There are two values here, but we should have one answer only. So which one makes more sense? So let's think about it. If we have minus 0.87, so here 1.5 minus 0.87, it doesn't make sense. It means the string does not extend. Instead, it stopped before the string reached its original length. So by using logical thinking, it doesn't make sense at all. But if you use this other value, which is 2.07, it does, because it extends. The extension is 2.07 and it's a positive value, so which means it extends by 2.07, so it makes sense. So the answer will be x equals to 2.07, and since we use g, right, so we get 2.1 meter to two significant figures. So every time when you do quadratic equation in this kind of mechanics question, it's really important to find out which make more sense to you. For B, magnitude of instantaneous acceleration of P at A. Okay, so at A, although the velocity is 0, but there will be tension. Try to pull the particle up, because without tension, the particle will continue to be pulled by the gravity down to the ground. So there must be a tension which try to oppose the gravity. So here we can draw another diagram. By drawing another diagram does not do you any harm, and it doesn't waste you any time, but it actually gives you more understanding about the question. So there will be tension here, and the weight, which is mg. So in this particular situation, I will put going upward as positive. So the resultant force will be equals to ma, and tension minus, because mg is going down, right, so it's minus mg equals to ma. By using Hooke's law, we know that F is equals to lambda x over L. And as I said in the last video, which is about the elastic strings and spring, the force is actually call it as tension. So here we can use T is also equals to lambda x over L, and lambda is 14.7 times x. So the extension, we have found the extension, which is 3 plus 3 square root 6 over 5 divided by the natural length, which is 1.5, is equal to 20.3 Newton. For this particular answer, it doesn't have fractions, so it has a lot of decimal. It's better to keep all this decimal in the calculator, because it's quite important. So T, which is, we can write it as 20.3, but in calculator we use the whole value, minus mg, m, which is 0.6 g equals to 0.68. So A will be equals to 24 meter per second square to two significant figure. So as you can see here, when the particle pull the string and it reach instantaneous rest, it will have a maximum acceleration, and we will see this kind of things more in simple harmonic motion. So here's the last question, which is quite easy. and it's easier than the last two questions that I explained just now. Okay, so a particle P of mass mg is attached to one end of the light elastic string, so there won't be any compression, of natural length a, and the modulus of elasticity of 3 mg. The other end of the string is attached to a fixed point O. The particle P is held in equilibrium by a horizontal force of magnitude 4.3 mg applied to P. The force acts in the vertical plane containing the string as shown in figure 1. First, find the tension in the string. There will be a tension in the string. Imagine we have theta here. So this will also be theta. So by taking right side and upwards as positive, for y-axis, F will equals to ma. And since the whole system is in equilibrium, so there won't be any acceleration. So the resultant force will be equals to 0. So by resolving this towards the angle, we get t cos theta, which is upward, that's why it's positive, and minus mg equals to 0. So t cos theta will be equals to mg. Okay, next we can try to solve the x-axis and equals to 0 since there's no acceleration. So 4 over 3 mg will minus t sine theta equals to 0. So t sine theta will equals to 4 over 3 mg. So this is the first equation, the second equation. So we don't have theta, so what can we do about the theta? Here we can square both of these equations and add both of these square equations together. So the first equation square plus the second equation square, which is t square cos square theta plus t square sine square theta equals to mg square plus 16 over 9 mg square. So by factorize the t square, we got cos square theta plus sine square theta to 25 over 9 mg square. So here cos square theta plus sine square theta is actually equals to 1. So we know that t square will be equals to 25 over 9 mg square. So we can square root both sides. T equals to 5 over 3 mg. Of course, if we square root both sides, we will have plus and minus. Okay, so since in this particular situation, our tension is going upward, so your final answer will be T equals to 5 over 3 mg. So for B, the elastic energy stored in the string. So here, we know that EPE will be equals to lambda x squared over 2L. But we don't have extension, so we can use Hooke's law. T equals to lambda x over L. And since T is 5 over 3 mg, which is equals to lambda, which is 3 mg, x over A. And we can eliminate mg, so we get x equals to 5 over 9A. Now we can find the elastic potential energy. So lambda will be 3 mg. So 49A squared over 2A. So 3 mg 81A squared over A. So we can eliminate 1A and the 3. So we get 25 over 54 MGA joule. So the elastic potential energy is equals to 25 over 54 MGA joule. Okay, so that's all for this video. If you did learn something, please leave a like and subscribe to my channel. And I hope I will see you in the next video.